The title of our work is Perimeter Defense Game Between Aerial Defender and Ground Intruder. This work was done by University of Pennsylvania and George Mason University. Here is the outline for the presentation. For the introduction and related work, we address the perimeter defense game from pursuit-evasion game. What is pursuit-evasion game? There are two examples below, the tag chase game and the late in the lake problem. There are pursuers and evaders in the game, and the state dynamics are shown below. Here are the parameter space for search and pursuit evasion. And you can see that there are many variants of PEG. As for the related work, here are all the 2D case of the game. We can have 3 players or voronid neighbors, and we can also consider the presence of obstacle. And there is a target guarding problem. And when the target is a parameter, we call that as a perimeter defense game. Here is the perimeter defense game with a 1 versus 1 scenario. And here is the related work in perimeter defense with a 3D extension. We can have a multiple defender or intruder. As for the problem formulation, we consider the ZD and ZA as the spherical coordinate of the defender and intruder. And we also have a gamma and omega for the speed of the intruder and defender. The speed of defender is characterized by this equation. And the state, we are interested in the Z, which we define as the psi phi r, where the psi is the difference between psi of intruder and defender, and phi is the phi d, because the intruder is on the ground plane. Here we define the defender's maximum speed as 1, and also we define the ratio of the 2 players as variable nu, and we consider the nu smaller than 1 because we assume that defender is faster than the intruder. And here the state dynamics for this problem. We define some terminologies. First, terminal time is the game ends at time tf. We can define this variable so that we know when is the condition for the game to end. And game of kind is defined as the question of whether intruder can reach the parameter. We define candidate strategies. As for the objective function, we define breaching point marked by B. It's the point where the capture occurs. We also define the payoff function. So here we define tau D and tau A as the time for the defender or intruder to reach to the breaching point. And the difference between those 2 time is the payoff function we are defining here. And we also call a large omega and gamma as the control inputs and strategies. So we can change the payoff function equation, change to using the control inputs and strategies. And we can express this as a Nash equilibrium with where the either omega star or gamma star indicates the optimal strategy. And optimal payoff here is P theta, which is given by the payoff function when the optimal gamma and omega are here. So candidate strategy for defender and intruder is to move towards the breaching point. So here we address this as a candidate strategy, and we will prove that this candidate strategy is actually the optimal strategy. So here we generally express this tau d and tau a using some geometry. And finding optimal breaching point is the key for optimal payoff. So we will try to find that optimal breaching point by relating the variable beta and theta, which is defined by the marked angles shown here. And we see that because theta and beta is one-to-one mapping, if we can have a just the two equation for finding those two variables, we can have a unique breaching point. So by lemma 1, we can construct two independent equations, and we will solve for those two parameters to get the optimal breaching point. So the first equation comes from the optimality of the game. So here we just assume that there is optimality. So taking the derivative of the payoff function, we set it as a 0, and we solve for this quantity as a beta, and this will relate the beta with theta. And this is the first equation. The second equation comes from the geometry. We focus on the triangle and using the lower cosine, and also using the remark 2, we can express the second equation relating the theta and beta. So from these two equations, we solve for optimal breaching point. And definition 1 says that those variables satisfying those two equations is actually optimal approach angle as beta theta, and also optimal breaching point. Yeah, that's relating the theta and beta star. And optimal payoff we can also express as the using the parameter theta star as shown below. So let us prove the optimality for this game. We first will define the winning region and also prove the optimality. So we prove that the barrier for the game of kind is given by a simple closed curve with this quantity is 0. So barrier meaning if we have some winning region, that will separate the two region where if the intruder is inside that region, intruder is always winning. And if intruder starts outside the region, the defender will always win, or they have at least optimal strategy for them to win. And we also have this corresponding position ZA that makes P theta as 0. So meaning that we will try to focus on this region with a P theta 0, that we will actually argue that this is the barrier or the winning region. So using some other lemma, we can define the winning region as shown here. And for the proof of optimality, for the left part of the Nash equilibrium, we prove the conservation of payoff, where along the barrier curve, the payoff remains the same. And then, yeah, you can follow through this lemma. Basically, when they are approaching the breaching point, then the payoff should stay the same as well. And degeneracy happens when phi d is 0. So yeah, in this special case, we say that the optimal defender strategy is to move towards the optimal breaching point at its maximum speed. And in this lemma, we prove the smoothness of the curve. And using that, we go through the extensive geometry and also the previous lemma to prove that as a generalization, this statement is true. And this is really important because it's corresponding to Nash equilibrium, which means regardless of intruder's behavior, defender, if continues to move towards the optimal breaching point, then yeah, the quantity P decreases or stays the same, which we wanna have for the result. And for the right side of the Nash equilibrium, we can also argue that using the similar argument, intruder strategy is the move towards the optimal breaching point at its maximum speed at any time. For the detail, you can refer to the paper for the detailed proof. So we run simulation to verify the optimality. We prepare 3 setups. When both defender and the intruder follow their optimal strategy, only defender follows or only intruder follows. Here is the initial configuration. And first condition, you see that all the agents are approaching to the optimal breaching point. And here, only defender follows the optimal strategy and intruder seems random. And here, only intruder follows the optimal strategy. Here is the result for simulation. The top, it shows the time burst target time curve for each case. And this is the trajectory for the defender and intruder. We see the first case, the payoff stays the same as 0. And for optimal defender strategy, it decrease. And intruder case, it increase. So we verify the Nash equilibrium. So conclusion, we solve the perimeter defense game on a hemisphere. We propose an objective function, and we take geometric approach and define the winning region, and simulation verifies the optimality of the game. So future work will aim to solve a perimeter defense problem between aerial defender and aerial intruder. Thank you for your attention.